All right, time to get back. So this was more a logistic break. Okay, so this is the review that we were talking about, right? Everyone is familiar with independent random variables, right? Yes? What else? It's going to be very useful for us. The product rule. So here we have this. By the way, I'm introducing now this notation, but when I'm using this notation, we are not talking about probabilities on events. These are actually distributions or probability density functions on random variables, right? So this is a little an abuse of notation. You can assume that all these P of X, it's not that, oh, what is the event X? What is the event Y? This is a distribution, okay? And in this case, X can be, I don't know, our state variable. Or it can be anything, but it's basically a real value number, right? It's not an event. This difference matters, but since we are not going to be mixing things, I think it's fine, right? But all these, let's say, topics that I'm now writing here, they are usually presented, right, just for events and usual courses, right? But, okay, what I'm doing here is you can also rewrite them, and then they are still true for distributions. So, okay, we have the independence, right? Very important property. It's going to be used anywhere, as much as we can. So, actually, the first thing you always try is assume that variables are independent, and then you see that they are not, but then this complicates a lot. We'll see what to do with that, right? So another important one is the product rule, right? So if variables are not independent, then what we have basically, it's this well, kind of equality, right? We always know that the joint probability it's going to be this, the probability of one of the variables conditioned by the other, right? Multiplied by the probability of the second random variable. Okay, total probability. This is also very important, but you will see, don't worry. So basically here we have a joint distribution, two variables, and then what do? We simply marginalize one of them. So this is all, we are also going to use this word a lot, marginalization. And this is basically what it is. So we take one variable and then we marginalize. We take out of our state variables. So this is a way of saying, look, we don't care about the Y variable. We are just going to evaluate on all the possible values. And then the result is going to be this posterior distribution, right? So this is on this lecture that I put on Canvas, if you want to find out a little more. Okay, what else on review, right? So we have the same thing, but now for condition events, right? So let's say that we want to calculate this distribution, and what we have is just a joint distribution of this, right? So this is still the same. We are marginalizing, but in this case, this is a condition. Okay, so this is just review. Please don't think that I'm going too fast. I'm probably going too fast, if you do. But this is a review, so everyone should be familiar. If not, maybe ignore this part, go to the lecture in Canvas, then you will follow all the things, and it will be much more clear. Also, if you have any questions while I'm explaining this, just raise your hand. I'm going to try to ask, like, at some points, like, thumbs up checks. So if I ask you, are you with me? Thumbs up. If this idea is clear, please tell, right? This is important because some things we should not move on if they are not. But on this point, everyone is good, right? So these are just review of past things. Thumbs up if you are like, this is like boring. You have seen this many times. I'm just writing for the nth time. Okay. And then what else? So, the reason we are doing this, and I'm not writing on the blackboard, is because all these classes with blackboard cameras are terrible. So we try to find a way, so we'll see. If this works, excellent. If not, well, you were testing individuals. Okay, so, oops, very important. Bayes theorem. Again, this is true also for distributions, so it's not, but we will be using this for some derivations, right? So everyone should be familiar with this. So it's this. Has anyone obtained the Bayes theorem from the product rule? Have you done this experiment at some point, you? Okay, awesome. No one else? Okay, yeah. Yeah, so you can. But this is from more basic courses, I guess. And then here we can also write it this way. Okay, so this is a review. Again, we'll be using these kind of properties or interesting qualities, but they should be known, right? What I'm going to introduce now is also that something that should be known for everyone, right? Which is the expectation operator. We are going to be using this a lot also, right? But everyone is familiar with the expectation operator, right? Okay, so just because this is a little more important than the previous points, I'm going to start defining it from the beginning, right? And you will see that it will appear in some things like later, tomorrow, right? In the following days. But with this, we have proper definition, right? So we'll have this definition, the expectation operator. Okay, so what it is? This, I'm writing it this way. Maybe there's other kind of, so people write also like from which distribution you are considering this operator, but let's put just this definition as it is now, clear, right? So it corresponds to this. So you can imagine this as a kind of weighted average, right? So forget about the integral, right? So this is the limit of a sum. But you can consider that what you are doing here is a kind of weighted average of this variable, right? So this is used a lot. Actually, this is the first order moment. Many places ask you, okay, so what is the expectation of this variable, right? You even hear this on the news, right? Expectation of. Okay, I don't want to say this, but expectation of viruses, okay. Right? They are giving statistics. Okay, anyway, so we can also write here like this corresponds to a mean, right? So it has like interesting properties. Basically, it's a linear operator. And we don't care too much, right, about, but some of these properties are going to be very useful, right? So let's just define them today. Okay, so, well, the first thing is that, yes, this, it's a linear. And, okay, so what happens when we calculate the expectation of a constant variable, no random variable? It stays the same, right? So there's no distribution, or let's say that this distribution for this, there's no, it's a constant, so you can imagine there's nothing here, you just take it out, and that's going to be useful, right? So, but who wants to do the expectation of a constant variable? Probably no one. But we might want to calculate the expectation of a random variable multiplied by a constant or a vector. Matrix, anything, right? But basically something that is not a random variable. So for this also, this is going to be used a lot, right? We can just take it out, right? Again, this, you can demonstrate this. If you go to the definition of the operator, you come, you take it out, right? Okay, so what else? Okay, I'm not sure if this is useful. I think no, but still, this is also trivial if you put the... So you have a random variable. Okay, now it's a random variable. Okay, now it's not. Yeah, you're just assuming a constant. Fine, you can just take it out, right? And then this one, it's actually going to be very useful. So now we have the summation of two random variables, right? And although this looks trivial, it's not exactly, I mean, there are things happening, and I'm going to show it now. But basically, this holds always for any distribution, right? So you have the summation of two random variables. It's equal to the sum of their expectations. Okay, so since I said that it's going to be important to manipulate like expectation, at least at the beginning, right, because these are the foundations that we'll need later for a proper state estimation, I'm just going to show this, right? So, okay, we are going to just like expand like things here. So what does this mean, right? This summation of these two things equals this. Right, so we have the two random variables, right? And then we are going to do the same weighted kind of sum or integral, right? But the problem now is that we have two distributions, right? So we need to do this with respect to the joint distribution of these two things, right? So from here, basically, we are going to do some manipulations, and then we are going to get like this result that this integral, actually, if you do some things, you are going to get like these individual expectations, right? So, okay, let's go. These are just a summation, so what I can do is separate this, right, in x and y. Right? And then, since these integrals depend on some variables, actually we can move, right, depending on which variables we are integrating, right? So for instance, we can have this, which only is dependent on x. This depends on both, so you cannot take it out. And then we are going to have this. And the same goes for this side. And then can someone tell me what is the name of this property that we just growed before? Oops. Oh, I'm getting used to right here. Right? So this thing here, right? Do you remember that I said marginalization? Exactly. So marginalization, it's going to be used many places. This is the first one that we see, right? So, okay, might sound trivial, but this is great because this is actually equal to this. Okay, so, and then I think we are here, right? So we have already, and the same goes here. So it's kind of natural. Yes, it's a linear operator, but the thing that happened underneath was not that simple as just, yes, we just separate things inside, right? So we need to be careful with this operator. I'm sure that you have done thousands of exercises, right? Because, I mean, in undergrads or depending on your bachelor's, this is kind of common thing. Maybe for some of you, or maybe you just were introduced to this. But this operator is tricky, right? So you need to know that behind there's actually an integral, right? It's not as simple as start manipulating things. We can do that once we are like comfortable enough, and then we know exactly. But the thing is that inside there's an integral happening. Okay. So it's a little slow moving. So we show some properties that are going to be useful. Let's show like some anti-properties. Oops. By the way, the thing was clear on the integral. If not, you can redo the exercise, and there's going to be new exercises for practicing later on this lecture, right? So if you feel, oh, I'm going to practice a little more, I'm going to give you then later what happens with the multiplication. But okay, this is probably advancing material. Some anti-properties. Right, so this one is, in general, a tricky one. I talk about the multiplication, right? This is our wish list, our wish that, yeah, if things are like this, then many things become simplified. But in general, this is not true. So we'll see what can we do with this. Basically, this raises the complexity a little. Anyway, now I'm going to define, it's not really an anti-property, but this is an important concept, right? What are uncorrelated variables, right? So if x and y are uncorrelated, right? I'm going to define it later, right? But basically, this is another consequence of being uncorrelated, right? Its cross covariance is 0. Then this thing that we have just described, this thing holds. Okay? And then there's a little side note of this. If x and y are independent, so independence, it's a nice property we have defined before what happens, right? So the product rule becomes like trivial. In general, we want like independence, but the world is complicated. It's not just uncertain, right? It's intricate. These relations between variables are not always obvious. So in general, you can assume that yes, they are independent, but then you see what happens. But okay, let's see. So x, y are independent. Then they are also uncorrelated, right? And this is going to be useful because sometimes independence is a stronger property than uncorrelation. Okay. But the problem is that the reverse might not be true, right? So if two variables are uncorrelated, maybe they are not independent. Yeah, I'm not spelling this. So in general, might be true, right? That, and I think for kind of standard distributions, not very exotic, this is true, but you need to be careful, right? So when someone is asking, oh, you have an independent variable or you have an uncorrelated one, be careful with this. Okay, so now we are just talking as one-dimensional random variables, but in general, this is going to be more than one. Right, that we're interested. So basically, we'll have a vector of random variables. So what is the expectation? Of a multidimensional random variable? Right, so let me write it this way. Let's say that our random variable, now it's not, single-dimensional one, but we can write actually a vector of this, right? So in this case, it's 2 dimensions, x and y. So this is not, oops, it's not writing. This is just going to be this, right? So the individual expectation of each of them. Right? So imagine you have 1,000 variables, and they're asking you, okay, so what is the expectation of this? You can just go one by one and then calculate at least the first moment, right? So each of them is the individual value. Okay, so more definitions. Again, take this course, take this class as something for the future in the course, right? So this is going to be helpful. It might be a little dry if you have already studied these things before, but again, you will feel, not in this class, but later on the next class and then the following one, that all these concepts are actually paying off, right? Because if not, it's very hard to define like the problem like properly. Okay, we also have like this concept of conditional expectation. Oh. Yeah. By the way, is someone using the notes from Canvas? You have opened them? Okay. So what is better for you? Like writing, taking a look at the screen? Okay, okay. So you have the file also for tomorrow's and Thursday's class. I've seen also some people that, okay, because maybe I'm grading here and maybe you don't want to grade everything, that what they do is they printed the notes and then they come and they just write their own comments. So this is also something to think about. Okay, so, oops. Yeah, conditional expectation. So the same thing, right? So just to have like notation a little clear, what I'm doing here is this. I'm just writing the expectation of the variable x, but it's conditioned by another random variable. So what this means, right, and this is just a definition, is that okay. Right? So it's important because then you see a lot of people just writing directly like the expectations, and you need to know exactly what they are talking about, right? So exactly the expectation with respect to which distribution, right? So in this case, well, we're writing this, but again, there's other ways of representing this. So maybe just write x here, and then some people just write here like this, but well, these are other conventions. So we'll follow this one. Oh, it's too hot? Too cold? Too cold, yeah. Okay, let's try to make the class warmer by thinking. So what else? Let's move on a little. So for the expectation, you have one question. X and y are both random variables. This thing. Yes. Okay. So now let's discuss a different topic that it's also going to be very relevant for us, right? So it's covariance. Right, and in this case, it's in scalar form. Okay, so usually this is also called autocovariance or variance in general, right, for a single variable, but let's define it like properly, because, well, you will see now that later there's, right? So when someone talks about this, like auto covariance or just covariance, right? But, oops, from a single value, so we are going to be referring to this, right? And basically, the definition also comes from the expectation operator, right? So, I mean, this is a single value, so. Right, so here is the random variable. This is the expectation we calculated before. This is just a standard definition. But again, this is going to be very useful. And we'll show like examples later. It's not just a mathematical definition, right? Especially when you want to estimate like covariances of random variables. The definition comes very handy. We can talk a little about this. So if we expand this thing, right? We are going to have something like this. You can do this at home if you want, right? So, okay, is it? Yeah. So although there's a minus sign, this thing it's always positive, and this is going to be like one of the a very interesting property, right? So this is always. Whoops. Okay. Right. You will see what happens in the multivariate form, right? This is going to have like a different property, but it's still the idea is the same, right? So why is happening this? Because this term it's always right. This term doesn't matter the sign; it's always going to be a square. So the result is going to be positive. Again. You will see the properties on this just tomorrow. Actually, it will allow us to use like a different factorization for matrices, but this is very, very helpful. Okay, now this died. Okay, so if things don't work well, now I need a microphone. If not, if you see this video, you will not see. Okay, so we need to find the exact logistics. Let me work on this. But maybe we have like some microphone to move, be closer. No, for the next class. Okay, yeah, so Wi-Fi, it's very unstable. I don't know if any of you have tried to do like some settings with Wi-Fi conditions. I'm sure. Right, you go there, nothing works because there's 10 more Wi-Fis there jamming your space. Yep. Okay, anyway. So now let's define cross covariance, right, from a single variable, right? So I'm just going to write it like this. Usually I'm not going to write like this name, the covariance, right? This is very general. But this, I think it's a little more explicit, right? So cross covariances are going to be important when we move to the multi-dimensional state variables. And then the definition, okay, so okay, so this is just the definition. Now, I think let's move to the more interesting part, which is the vectorial form. So, if the expectation of the, let's say, vectors of random variables was easy, you just stack them and then do the expectation of each of them. For this, it's also going to be a little convenient, you will see. Okay, so let's start with covariance. We can also write it like this way, right? In general, I think we are mostly going to be use this capital epsilon, right? No, this is not epsilon, sigma. Okay. Okay, so again, the definition, just to have everything well defined. It's kind of similar, but there's going to be this little problem now, right? And I think that's where you need to start thinking in more in matricial form, right? We don't have like real values, but actually we have vectors, right? So if you can imagine, actually this helps a lot. If you can imagine this, this is a vector, unidimensional, I mean, a column vector, right? And basically, we know that the result of this should be, well, okay. So this is this way. We cannot really multiply vector by vector, right? This is, I mean, not well defined. So basically, the definition of multivariate requires this to be transposed. This is also equivalent to an outer product, right? And the interesting thing is, that's what I'm saying. You need to start thinking on matrices ways. The result of this is a matrix, right? So dimensions on this vector are going to be the same, right? And then you are going to have a nice square matrix n by n, right? So again, just the definition and the little difference with respect to the scalar form is this transpose, right? But we're always, covariances are always like these square forms with sort of outer products of these little errors, right? So you always need to have, as a result, if it's a multi-dimensional random variable, you should also always have a matrix. Unless it's on a scalar. Okay, and then let's define cross covariances. In this case, I'm going to refer to this as cross covariances. I'm going to discuss now, after giving the definition, little subtlety of this. Right, so again, yes, you can define it as covariance of this. And then it's going to be the same definition as before. Right, and I think we can we can comment several things on these cross covariances. The first one is, so what can you tell me about the result of this? Imagine that you have like, so do these dimensions have to match? You say yes. Who says yes? I mean, the dimensions on X and the dimensions on Y. Okay, this is Y. Do they have to match? No. Right? So this is interesting because covariances always give you square matrices as results, but cross covariances can be anything. Imagine that Y is just a scalar value, right? So at the end, or a different one, at the end you will get like a rectangular matrix. Another interesting thing is that you can consider cross covariances as block matrices inside of your covariance, right? So imagine here, this is a monstrous state variable, right? And then someone is asking you, okay, so I want to know cross covariance on these variables. Not all of them, right? I don't want to know the covariance on the 1,000 variables you have, but just the cross covariance with respect, I don't know, this or maybe this part, right? So then they are going to be like block matrices, right? And the definition is true also. I mean, the second definition that I gave on cross covariances are going to be parts of this because they are also included. So in general, we are going to talk about covariances, right? But you need to be careful exactly when we are defining like variance that includes all the state variables, and then you will have a square matrix. And when actually it's a cross covariant, actually just matching these variances, right, with respect to different parts of your state variables or different random variables. Don't worry, I think the best way for this is going to be problem set 1. So, and problem set 2, yes, a lot. Because there you will see exactly these things in action. But I think for now, it's just good to have the definition, knowing that, okay, single variable, it's fine, the definition, but for more variables, we start talking about matrices, right? Because it will fall naturally that we'll go into linear algebra cool solutions, right, that will help us solve problems. The first one, it's going to be just the covariances, uncovariances. Okay, so yeah, I'm going to give an example because I have it here. I'm just going to expand these cross covariance, right? Right, so this is going to be useful because we are going to work a little with the expectation operator, and then if you don't feel comfortable with this derivation, you can do more at home, right? But the idea is that you should feel comfortable now with the expectation operator. This is probably one of the things that we are going to be using a lot. I mean, it will come naturally, don't worry, don't be afraid. But I think it takes some practice. Okay, so I'm just expanding this. Okay, so I'm just going to multiply element by element, and then we are going to see like how many terms we have here, right? So if I multiply element by element, let's say that I start this way, right? Then I have second element. So, okay, what I'm doing here is I'm multiplying this against this, and then against this, right? And then I'm going to take this guy here. Actually, I have colors. Yeah. And do this. Okay? So, let's go. Okay, this is very slow. Okay, so as I said, this is the first x multiplied by the first element, and then here we have this, right? No surprises. Then we are going to have this multiplied by x transpose, and then we are going to have okay, I think this is a bad idea. No. Okay. Right? This last term is just a multiplication of both expectations. Okay, it was a little bad, but it's clear, right? Okay, so then let's use like some properties on the, is it clear? No? What? You have some, oh, okay, okay. So let's just use like properties on the expectation operator, right? And the first one is we talk about linearity, right? So what we are going to do is we are going to write like different expectations, right? So this is one. Okay. Okay. This is the second one. Okay. Third one. I'm just grouping things here, but you will see that we'll get like some things simplified. And then again, yeah, we have this fourth term, which is going to be right. Does it matter if I transpose the result of the expectation of or the expectation inside, like putting this guy here? No, right? Okay, so start thinking in terms of matrices. It's going to be helpful. Okay, and then let me rewrite it again. So we cannot really do much on this guy. On this, we can actually separate this, right? So these are different random variables. Okay, then we have the same thing here, right? So in this example, the expectation of the expectation, okay, so this gets out, basically this thing, right? And then we have this. And then we have this term that, okay, it's just the same, right? So again, so why is happening this thing? The expectation of a random variable is constant, right? Everyone sees this. So we said that one of these nice properties is, okay, so you just have the constant expectation, a little silly, but hey, we are using it here. So it was not that silly. Okay, and then, well, after this, I'm gonna use some color. Yep. So these two things go away, right? So we have sinus minus and plus, right? These guys go away. And then the final oh, no. Here. Final result is something that actually I described before, right? So this, okay, I'm gonna rewrite it, exactly the same thing. But do you remember what I said when I was saying, look, a variable that is uncorrelated, it's only when there was a property that hold, right? So what is the only way? And remember that this equals this cross covariance. So what is the only way to make this guy 0, right? This covariance 0, is make this equal to this. Right? So this was the property on being uncorrelated. So if you want like cross covariances or random variables uncorrelated, then this is the result that you need, right? So this expectation here actually equals this thing. If not, it's always going to be something, right? And that's actually what you're interested in calculating. What is exactly the cross correlation between random variables? Redo this experiment, I mean this expansion at home, right? I think it's a good exercise. Okay, yeah, I'm almost done. I hate to start the first class like writing math, but I think it's good because you can choose this. Well, no, I choose this better than doing a very, very intense course tomorrow and on Thursday. So I think this way it's a little introduction, you see a little how it works. Tomorrow you will become prepared, so if you want to print this, you print it. If you want just to take a look at the PDF, you can do it, but you get a taste of this. And I think all these concepts are kind of old, right? So I'm just renewing things. Okay, so there's an interesting corollary after doing this, and this is going to be very, very important for us, right? So covariance of a vectorial random variable is symmetric. Right? So that means that right? In this case, don't worry about complex variables. So far, we will just be using real numbers. But okay, in general, this is not symmetric, right? The property is Hermitian. So, but we are in the real world. We have real numbers. As I said, we are just going to be using those parts that are actually like relevant for us, and forget a little, but the field is like a little more wider than what I'm explaining here. Okay, so this is symmetric, right? And this is also important. What about this guy? Is symmetric also? No. Yeah, I mean, just to begin with, it's not square. So that's bad, right? But this is important, right? So it can be a subblock, but still, this can be non-symmetric. Is not symmetric. Okay. Okay, so if you want a proof of this, there's always a case where you can do a cross-covariant symmetric. But in general, they will be not symmetric. So you can find an ill-posed thing where, yeah, you do things symmetric, although they are not the same random variables. But that's a very strange thing. In general, just imagine, just change the dimensions on x and y. You have a rectangular matrix. That means that that's not symmetric. So this is a very easy way of finding a counter. But yes, in general, they should not be, although you can make it out. Okay. Yeah, we're interested more in general concepts, but there's always ill-posed cases. Yeah, that's. Okay, so let's say that here it's a zero mean random variable, right? You do this, and then let me expand it this way, right? So in this case, let's say that we have 3 variables. Right? And if you start doing this is a thought experiment, right? We are calculating covariances with the power of our multiplication algorithm running, and not very high dimensions, by the way. If you start doing this, you will see that, so this is simple, right? This kind of outer product gives us always like results like this way, right? So in this case, you have x1, x1. The diagonal, it's always the same thing multiplied by itself, right? And then the interesting thing is that when you look for this element in the matrix, so what you have is this, right? This element multiplied by this element, right? So you will have x1 multiplied by x2, and when you find this guy, it's simply changing a little the order, right? So you have x2 multiplied by x1, but we are multiplying here scalars, right? And for scalars, the multiplication is commutative. It's not true for matrices, but each of these elements at the end, at the end, it's the result of a scalar multiplication. So that means that here, you have, okay, 1, 2, and 1, 2 also. So you build it and you see. How is this going to affect us? You will see, but being symmetric actually helps a lot. Okay, there's a second corollary, which is also convenient. It's not, I guess it can still work if it's not this way, but you will see that we can choose like proper matrix factorization that are specially meant for this kind of property. Okay, so let me define it now, right? So we said that this covariance is symmetric. The second one is positive semi-definite. Well, semi should be positive definite, but properly speaking, yes, it's semi, because there are some ill cases. Okay, forget about this. So who has heard about this property, right? Many places, yeah. Okay, so this is the equivalent that we said before, that the covariance is always positive, right, for a scalar value. So this is equivalent for matrices. What is the definition of this, right? So you have any vector, you multiply by this matrix, and this is always going to be, so this is positive, semi-definite, right? So this is definition. Any vector, okay, You multiply it, and the result is going to be positive, right? So it's kind of cool. We don't see now a utility, but we'll see that there's a factorization that is meant for these kind of properties that will be very helpful. Okay, so, well, there's also a proof on the notes if you want to see it, but it's kind of based on the same principle. So you see that the expectation, it's always kind of a square form. There's always something multiplied. So if you do some manipulations at the end, you will get always a positive number. Okay, so another very interesting thing, now that we have defined the properties of covariances, so what happens in reality, right? Does these covariances appear from somewhere? They are given. We'd actually be interested in estimating them, right? So this is also an important topic. So I'm going to define now sample mean and sample covariance. Okay. So let's say that we have this random variable, right, xy. These are, let's say, our samples, and then they are independent and identically distributed. Oops, that's too many eyes. From this distribution, P of x, right? So this will be like the result of, I don't know, tossing a coin, taking a look at our sensor, temperature on this room, right? So we have several sensors or different instance of time. We need to assume that they have been sampled independently. Right, so when we have these kind of properties, by the way, it's very hard in reality to have like really samples sampled from independently from a distribution. There's always a correlation. But okay, this is just theory. So yeah, they are ID, fine. This is going to appear like very often. I'm sure it has appeared in many other courses before, but again, these are like nice properties. When you have these, good things happen, lots of simplifications. If you don't have these, well, you need a little more workout on the estimation. Okay, so sample mean. I'm just going to write it this way, right? And in this case, since we are assuming that they are independent and equally distributed, this is going to be equal to this, right? So you have all of them, and this is kind of a uniform average, right? There's a lot of variance on this. You can actually get this if you get, I mean, I'm sure that there's a course explaining this like very in deep, but actually this is going to be very useful, right? So this is the best we can do. All these samples have been sampled from the same distribution. They are independent. So this is it, right? You sum all of them and then you divide. Okay, again, I'm not going to derive this because then it will be a course on a different topic. But this is going to be very useful later for when we are like estimating like some variables. And then we have the same thing for the sample covariance. So we are going to get some samples, right, from this distribution. And then if we want to calculate the sample covariance, right, it's going to be exactly the same thing. Note that these samples can be not like scalars, but can be vectors, right? So that means that in this estimation of the covariance, it's going to look like this, right? So we'll have this, which is going to be a vector depending on the dimensions, and then we have the same thing but transpose, right? So remember, this is sort of an outer product, and as a result, we'll get a matrix, right? So useful thing you will see later, I think on problem set 1, there's here This little factor, I guess you can talk about one lecture, why you are getting this, and not by divided by n. But kind of the intuition behind is has to be with the dimensions, right? Imagine that this is a two-dimensional vector, right? So you estimate, no, not two-dimensional. You have two samples, right? Two samples. If you just have one sample, what can you say about covariance? Not much, right? Because here this is going to be 0, right? So you have perfect, or at least 0 covariance. But this is not a nice way of defining your covariance. You can just say something about your exact point. If you have 2, on the other hand, you can calculate what is the mean here. But if you think on the degrees of freedom, you have 2 samples. You have already used one for your sample, and again, this is more intuitive, right? The theory behind it's different. But you have 1 degree of freedom already used on your covariance, and you have the 2nd degree of freedom, which is giving you this 2nd sample to calculate this. So you cannot really use like the 2 samples as if they were there, right? So in fact, you need to weight like them properly. So that's why you are subtracting one of the samples, of the effective samples that you have to calculate the covariance, because let's say that you have already used them for the mean. Okay, I see some faces of surprise. Anyway, there's a proper demonstration of this if you go to statistical books. But is this clear? Thumbs up if sample mean and sample covariance is something that you can use now if I give you a bunch of samples? Yeah, okay, awesome. I think that was it for today, right? So today was like very just presenting concepts, putting some definitions. We still don't know what to do with them, but I think tomorrow we'll have a much more clear idea on what to do with all these concepts. So you will be applying these definitions to actually a more interesting topic. We'll be explaining Gaussians, but probably on a level of depth that you haven't seen before. Maybe some of you, yes, but it's going to be based on that, and many of these definitions are necessary, are the starting point. So thank you, and hope to see you tomorrow. See you.